So this next speaker is Richard Mandel from the Basque country, who will be talking about quadratic Diophantine problems in Baumslag-Solitar groups. And if you tell me to change slide, I will change slide at the appropriate time.
Okay, great. Yeah. Some of them have multiple. We'll
yeah.
see. Okay. So all right. Thank you, Alan, and thanks for the kind invitation. Okay, so I'd like to speak about some recent work with joint work with Alexander Ushakov. Okay, yeah, we can go to the next slide. The Diophantine problem is an example of a group theoretic decision problem. We can sort of trace the study of such problems back to as far as Max Dane's problems proposed in 1911. So I'll just click to the next. Might as well just go through the whole. Thank you. So right. So we have the word problem. We have the conjugacy problem. We also have the isomorphism problem, but that's not particularly relevant to this discussion. And one way to generalize these two problems is by equations. So the word problem and the conjugacy problem are both special cases of the Diophantine problem, which takes as input some equation, which is simply a word on the free product of a free group generated by variables and the original group, and outputs either yes or no, demands the output of either yes or no, depending on whether a solution exists in G. And there are variations. The compatibility problem asks if there is a solution in some group in which G embeds, but we're just talking about solutions in the original group G. So this is what we mean by the Diophantine problem. And one particular, okay, we can go to the next slide. One that might get annoying. I'm sorry. One special kind of equation. So the problem we will be talking about is the quadratic Diophantine problem. And a special type of equation is quadratic equations. An equation is quadratic if each variable appears exactly twice. Either you find an x in one part of the word and an x in another part, or you find x inverse in another part of the word. And there are other definitions where each variable has to appear at most twice, but we go with the strict definition where each variable appears exactly twice. It seems a little bit arbitrary, but these equations have very nice properties. Okay, so just to be complete with definitions, the solution is just a tuple of elements of G that you can substitute and get the identity. We can also think of them as homomorphisms from the free product of the free group on the variables in G, modulo the normal closure of the group word onto the group G. Next slide. Okay. So why are quadratic equations nice? Because it seems like a fairly artificial definition, but they've been studied extensively. First in the 60s by Matiasevich over free modelings, Edmonds and Comerford in the 80s, and Grigorchuk and Khrushchev in the 90s also studied them. And so in any group, we have this correspondence between the quadratic words and compact surfaces. I mean, this is just the standard way of looking at compact surfaces, and that gives rise to nice standard forms. There's also applications to the study of arbitrary equations over free groups, because they can actually be reduced to certain special quadratic systems. And this was established by Kovalovich and Yasnikov. And finally, they're interesting because they don't always solvability of quadratic equations doesn't necessarily correspond with solvability of arbitrary equations. You can have and there aren't that many examples known, but one can have groups with undecidable general Diophantine problem, the decidable quadratic Diophantine problem. One example is the free metabelian groups of rank greater than 2, greater than or equal to 2. Romankov established that equations in general are not decidable over such groups, and Lysenok and Ushakov proved that they are indeed decidable for quadratic equations. So that's one of the reasons why we like them, and in particular, the standard forms are very nice. So it's just very, very nice to study these kinds of equations, because you take an arbitrary quadratic equation, and you can very easily transform this equation into one of these 3 standard forms, and in polynomial time. So transforming the equation means obtaining an equivalent equation, and that simply means applying some automorphism which fixes the constants, and it's an automorphism of the free product of the group and the free group on the variables. So we're replacing the variables in the original equation with possibly products of variables and constants, and in the end we arrive at a really nice equation which has a solution if and only if the original equation has a solution. So we have these 3 forms. Spherical and orientable are basically the same, but I like to think of them as different forms, and they correspond very nicely with the classification of compact surfaces, which we'll explore in the next slide. So the standard form theorem, which is what was on the previous slide, it was proved by Edmonds and Comerford in 81, but entirely in a combinatorial way, and it's not the most pleasant proof to wade through. But nowadays one almost always thinks of this theorem in terms of as an analog to the classification theorem for compact surfaces, because the algorithm for transforming an arbitrary equation into one of the standard forms is exactly parallel to the standard algorithm for taking an arbitrary compact surface and transforming it into a nice form. So we have a polygon with edges labeled in like pairs of the variables and single edges for constants. This is going to give us some kind of compact surface with boundary, and the constants would be just the boundary components. And we can apply the standard algorithm to just keep doing cutting and pasting, and we eventually get a really nice form of this surface. And here's an example of one of the standard cut and paste moves, and it just it gives us an explicit automorphism, and then we just take the composition of all these automorphisms, and then we have our automorphism, which transforms the original equation into the standard form. Okay, so that's emulation, because this simply doesn't happen in other contexts. Like one could easily define cubic equations in the same way, but you don't have this kind of nice way to transform equations without blowing up the size of the equation. Here we have a very nice standard transformation. Okay, next we'll go on to the next slide. So everything that I've been talking about so far is just applies to an arbitrary finitely generated group. But in particular, we want to talk about the Baumslag-Solitar groups, which everyone is familiar with. The special cases that I'm discussing today are the unimodular ones, which is just Bsn plus minus n, and I will speak a little bit about the metabelian ones, so Bs1n. They're the only solvable Baumslag-Solitar groups. So the results. Alexander Ushakov and my results are related entirely only to these cases of the Baumslag-Solitar groups. Next slide. Oh, sorry, I was anticipating a different slide. But yeah, recent results, I'll just go through really quickly. So the Diophantine problem, and when I just write DP, it's the general Diophantine problem for systems of arbitrary equations. This was proven to be decidable, but only if you don't have constants in the equations by Lopez, Kolinkovich, and Myazikov very recently. And I mean, this version of the problem simply, this is the version of the problem where we don't have constants, and we require that a solution be non-trivial, because obviously otherwise the problem is trivial. So our equation is a group word, is a word on the free group on the variables, and we seek a non-trivial solution, which gives us a trivial word in BS1n. So this is decidable for systems of equations in BS1n. The arbitrary Diophantine problem for Bsn plus minus n, even where we demand that the solutions come from rational subsets, which are the images of regular subsets of a free monoid, that was proven decidable by Chobani, Holt, and Rees in 2020. And in fact, their results applies to a very large class of groups, which includes Bsnn, and they proved it for any group which is virtually a direct product of hyperbolic groups. So it's a very sweeping result, and it includes the Diophantine problem for Bsn plus minus n. And we have rational subset membership for Bs1n by Cadillac, Krustikov, and Zeche. And the knapsack problem has proven to be NP complete, as well as the power word problem in the complexity class TC0 by Kanardi, Lowry, and Zeche. So I've mentioned a few complexity results. I believe the following slide contains my and Sasha's actual results. So let's go to that slide. Okay. And yeah. Okay. So our results are that the Diophantine problem, for the quadratic Diophantine problem, in either Bsn plus minus n or Bs1n is NP complete, except for the trivial case where it's Bs1 plus minus n, 1 plus minus 1. And we also have a polynomial bound on the size of the solution. So if there is a solution, then there exists a fixed polynomial, which a cubic polynomial, which bounds the size of that solution if it exists. We could use the same polynomial for both Bs1n and Bsn plus minus n. So our results are complexity results. So I don't really have much time to go into NP complete, but so hopefully everyone's heard those terms. But if not, NP complete is just a really nice complexity class that is widely believed to imply that there is no polynomial time algorithm that decides the problem. So we don't know for sure, but whether or not that's true is dependent on the famous P versus NP problem, which is a famous open question. But NP complete problems are very nice because they all reduce to one another, and they're supposedly hard. We can be fairly certain that there's no polynomial time algorithm which will work. To prove something is NP complete, you simply find one of the many known NP complete problems and try to to establish a reduction from that problem to the given problem. That proves NP hardness, and you also have to show that your problem is in NP, which means that there's an NP algorithm, a non-deterministic polynomial time algorithm. And what this basically means, roughly speaking, is that there is a proof that witnesses the positive instances of your problem, which is verifiable in polynomial time. So you need a polynomial size certificate or witness, and you need to be able to verify it in polynomial time. Okay, we'll go into the next slide. So in both proving NP hard, so now I'm just going to talk about BSN plus minus n, and in proving both NP hardness and that the problem is an NP, we need to use the geometry of this particular quadratic equation. And, discussed it a little bit earlier with compact surfaces. So if we have a solution, then we have some Van Kampen diagram with the equation drawn around the edge of the diagram. And this Van Kampen diagram, because it's a quadratic word, we simply glue together the pairs of edges according to their orientation. We get some compact surface with boundary, and the boundary is just all of the constants will be boundary circles. Just to make it a nice closed compact surface, we can fill in those holes with 2 cells. So we have a 2 cell for each constant, and we have some surface. The picture depicts a sphere, but some compact surface could be non-orientable as well. And since we're working in Baumslag-Solitar groups, I mean, in particular BSN, but in any arbitrary Baumslag-Solitar group, are the relation cells, which there's only one relation. They look like this band. This is several cells joined together, and we call them T-bands. This terminology comes from is used in any H&N extension. So our sphere in this case is just tiled with these bands, and the bands will necessarily either form circles or rings, or they will join a T in one of the constants to a T in another constant of the same. So they can't do much. Okay, so we'll be exploiting the very restricted kind of geometry here. Next slide. And we can go in the other direction very quickly. So we can start with what we call a solution diagram, and this is just any compact surface, closed compact surface, and it's tiled with the T-band relations and some group constants. So we just have 2 cells labeled by constants in the group, and the rest of the surface is tessellated with these relations. You simply cut the surface in a nice way, and you're going to get an equation. So the surface actually gives you a solution to some equation, some quadratic equation. Okay, next slide. I guess I'm running a little bit low on time, so I want to at least get through the establishing NP hardness for BSN. So can you do the next slide? Okay, so the NP complete problem that works really well here is called the 3-partition problem. I'll just describe it verbally. The input to the problem is a multi-set of integers. There should be a multiple of 3 of these integers, and we can demand that they be positive. And the problem is to decide whether it's possible to partition them into triples, each of which have the same sum. And this is not only NP hard, but it's strongly NP hard, which means that it remains NP hard even when the input is given not in binary, but in unary. So even when the input is sort of artificially large, we still have an NP hard problem.
I think, has Richard disappeared?
He's frozen at my end as well.
Okay.
The quadratic Diophantine problem, spherical equation, but and see it visually.
Richard,
So we have
for a minute or two.
on the next slide, there's sort of a visual representation of this, which okay, so our equation, it has a solution if and only if the input is a positive instance of the three partition problem. One way can be seen from diagrammatically, because if we have a positive instance, I mean it's a simple matter to sort of rearrange the equation so that we have they're sort of in the elements are in the right order, so that like A1 plus A2 plus A3 is the same equals A4 plus A5 plus A6 and so on. And then we can simply solve the equation that way, and it's a free solution. It's not. It doesn't even. It works in the free group. So you can read off the solution just from this diagram. And in BSN plus minus n, it turns out that because of the very constrained geometry, this is the only possible diagram. So if we go in the other direction, and now let's go to the next slide. If we go in the other direction, so we have a solution to the equation. It gives us a solution diagram, which in this case will be a sphere. To make the diagram simpler, we'll just remove the one of the cells, which is the outside. So the outside of this diagram is one of the constants, and the inside has to the outside is the right hand side of the equation, and inside is the left hand side of the equation. And because of the constrained geometry, it turns out that there's only one possible thing that can happen, and first of all, each of the isolated T letters has to be connected by a T band to the bottom of the diagram, and all of the sub-diagrams that this will form must be filled with exactly 3 of the B cells. And furthermore, by a simple counting argument, the T bands have to have length 0. So it turns out that whatever our solution is, it will necessarily give us the diagram on the previous slide. So that's the visual sketch of it. So I'm out of time. I unfortunately don't have time to do the NP certificate. So I'll stop right here. And sorry for going a little bit over time.
That's okay. Does anyone have any questions for Richard? Okay. Well, I had a question from a couple of slides back, which I'll go back to if that's okay, because I have power. So here you've got a picture of a sphere. Are the tiles actually tiling the sphere, or is it I wasn't sure what the picture was meant to be of.
Oh, sorry. Okay, that's right. The shaded gray area is tiled by, well, in an arbitrary over an arbitrary group. We just have the relations of the group, and in BSMN we have this these bands, which enables us to actually prove things, because the bands can only do so much.
All right,
well,
so the dark gray is the dark gray is the equation. Sorry, yeah, the dark gray is the group relators, and the light gray is the equation.
Wait, okay, no.
Well,
everything that's gray is relations, and the white circles are the constants.
Yeah. Okay. Yeah.
So.
Okay, that makes sense.
And the whole NP argument is basically reducing such a diagram to a system of linear equations, because you can, you can sort of, if you have a solution, then you have this possibly very complicated network of T bands. And if you forget about the lengths of the T bands, then those lengths can be the unknowns in a system of linear equations. And it turns out that this is a pretty nice system, and it serves as a witness to whether or not you can solve the equation.